Today I want to look at an example of a system where that is in equilibrium, but where sum of forces will not be sufficient to find out what's going on. So you have a ceiling, two cables A and B are supporting a platform, and there's a 10 Newton weight that is hanging in here on the side. The length of the bar is 1.2 meter, the mass of the bar is of 8 kilogram, and the position of the 10 Newton weight is at 30 centimeter from the right end. Okay. So your approach to this probably in general would be to just say, okay, that's easy. Let's use the sum of forces on the y-axis and we should be fine. Okay. However, in here you will find out very quickly that you will have TA and TB in your equation, and that therefore you will have two unknowns. So this is not the best approach. Okay. Instead, what we will do is we will use the sum of torque in order to solve the problem. So when we want to do this, the first thing, step 0, okay, as my colleague says, the step 0 is just to identify the object of interest. So what is the object that we're trying to study in here? And the object we want is really the bar. So our object is the bar AB. We're trying to find the sum of forces and the sum of torque for that object. Okay. Once you have this done, the next thing would be to identify the forces that are acting on the bar. So we want to identify forces. So in here, there's some of the forces that are easy to see. So there's a force in here that we'll call TA. There's a force for the string that is on the other side that we will call TB. There is the 10 Newton block that is applying a force in here. I'll call this one F box, let's say. And finally, there's the FG of the bar. And the FG of the bar, we could wonder where to put it. There's something really neat in physics that is called the center of mass. For a bar that is uniform, this will be straight in the middle. And it says that the center of gravity, so the point where you can assume that gravity is acting, is the same as the center of mass of the object, which in a case like this one would be right in the middle. For most of the case that we will see, all of the case that we will see, it will be like that. It will be just in the middle. So these are the forces that we have to deal with. The step 2 will be to solve the problem. And to do so, we want to use the sum of torque, which is equal to 0, and also possibly the sum of forces equation, which should also be equal to 0. So essentially we want to use Newton's first law for equilibrium. So we already discussed that starting with the sum of force was not the best idea, so let's start with the sum of torque. Whenever we do this, we have to choose a pivot. So we have our choice for the pivot. We could put it anywhere we want, but there are two clever choices. If we put the pivot either here at A, or we could alternatively put it at B in here, in both cases, we will get rid of one of the unknown, because if we put the pivot at A, then we see that the torque due to the tension A will be 0. And if the torque due to that tension is 0, it means that this tension will not be part of the equation. So it will simplify our life a little bit when we do the math. So let's try this. So we want to use the sum of torque to solve it with the pivot at A. So we start with this, sum of torque with the pivot at A. We know that this has to be equal to 0 if it is to be in equilibrium. So we would just want to go and add the contribution from each force. All the forces are perpendicular to the r vector, so everything will be already with moment arm or lever arm if you prefer. So let's start with TA. So for TA, we know that the lever arm will just be 0 meters. Then we have FG, and we know that for FG, the distance to the pivot will be half of the length of the bar. So this will be 0.60 meters. Then there's the box. The box we know is 30 centimeters away from this side, so this means that it will be 90 centimeters away from our pivot. So therefore I will have the 90 centimeters, which is 0.9 meters, times the force of the box. And finally we also have the tension B, which is at 1.2 meters, so we'll have 1.20 meters times tension B. Probably noticed that I left out all of the signs in here. Well, the first one we don't care because anyway this will be 0. For the second one, FG, it's trying to rotate the bar clockwise, so therefore we'll take it as being negative. So we're assuming that a positive direction will be counterclockwise, which is the classic convention. Same thing for Fbox, it will be generating a clockwise, so negative torque. And finally for TB, it's the opposite, so this one will be positive. So from this, we have all the values that we need. We know that Fg is just equal to the mass times g, so it will be 8 kilograms times 9.80 meters per second squared. So we know the value of everything. Fbox is 10 Newton, so we can solve for TB. And once we solve for TB, we will get the value of 46.7 Newton from this equation. Okay, you can do the math on your own. So this gives us our first value. And once we have that, then we can go back to the sum of forces. Okay. And in here we want to use the sum of force on the y-axis, which is equal to 0. Again, because it's an equilibrium. And for the y-axis, we will have TA plus TB minus FG minus the force applied by the box. And since we now know what TB is equal to from the equation before, Fg is still 8 times 9.8, Fbox still 10 newtons. So from all of that, we can find the value of TA, and you should get that TA is equal to 41.7 Newton. So that's it, okay? By using first the sum of torque and then the sum of forces, we were able to figure out the value of the tension in string B and the value of the tension in string A. And again, the trick, whenever we use the sum of torque equation, is to choose our pivot wisely so that we can get rid of some of the unknown so that the math will be simpler. There you go.